Thank you for coming back from lunch. So I'm Leslie Kaelbling, and I'm going to talk a bit about the embodied intelligence mission that's happening inside the Quest. And I'm actually co-leading this with Nancy Kenwisher, and I'm using some slides that Nancy and I made together. So I don't get credit for all of this. Okay, so fundamentally, we're interested in how people do really general purpose behaviors in the world. They build houses, they make food, they fix things, they take care of each other, they invent new solutions to problems. And we have really no idea how people do these things, and we don't know how to get robots to do it either. But we think that it could be useful to study the questions jointly. So that's what we're trying to do. And so what I'm going to focus on today is just a particular, I mean, there's more than 1,000 questions about how to do this, but I'm going to focus on one particular dichotomy of approaches. And the question fundamentally is, okay, we get images in and we generate motor control signals, but what goes between the images and the motor control signals? How do we think about that problem? So a problem, a kind of a canonical problem we've been thinking about is, I show you a scene with some objects in it and I say, well, there's an orange hidden in here somewhere, can you find it? Right? And the finding actually has to involve moving objects out of the way. So which object would you move? So one strategy, and right now really the overwhelmingly most popular and pursued strategy in robotics is to say, okay, that's cool. We'll train a neural network to take the images and produce the motor control, and that's what we'll do. So end-to-end model-free learning. It's model-free. Often people would call that network a model. We call that model-free in the sense that it doesn't have in its head a model of the world outside or a model of the effects of its actions. It's just a straight-up mapping from the inputs to the outputs. Alternatively, we could say, well, no, actually, we want to understand what to do by understanding what's going on in the world. And so we could say, all right, I want to look at the world and estimate the situation in terms of three-dimensional objects and their shapes and positions and so on, and then use some reasoning to decide what action to take. So we'll call that the model-based approach. Okay, so when I started working in robotics a long time ago, perception was terrible and it was completely a bottleneck and we could hardly do anything. But computer vision has just made these great strides recently. And this is an example of a system that some students in my group have put together, but there are many other systems like this now. What's interesting about it is it takes one image, so that one image in the upper corner there. It's an RGBD image, meaning it also gets readings of the depth at every pixel. But that only gives you a very fragmentary picture of what's going on, right? So this is the input signal. But from that signal, using pre-trained models, we can compute that completion, that thing that's rotating around on the other side, right? So from one view, we can make a pretty darn good estimate of actually what's going on in the world. And this is on objects that the system has never seen before. Okay, so building on that, we have put together a kind of very model-based, a very model-based control policy. It takes in images. It runs them through a perceptual process. It's not exactly the one I showed you, but it's very similar. It also can give you some semantic information about the objects. It computes good ways of grasping the objects based on the three-dimensional situation. It puts those things into a reasoning algorithm, in our case into a robotic task and motion planner that decides which objects to move, where to put them, and so on, and then it can execute on a robot. So this takes out images and it gives out motor controls, but it has a lot of intermediate modeling and reasoning about what to do. So I'll just show you working in a situation and then contrast the two approaches a little bit. So here's a case where, okay, so on all these tasks, the system has never been given this particular task before. It hasn't been trained. There's no learning. There's the perception and the planning. You can tell it in natural language what you want it to do, so throw the soda cans away into the bin. It does that, and you'll notice that it's not crashing into those big objects that are in the way, right? So it has, because it understands the 3D situation, it can avoid these other objects. here's a problem that illustrates something pretty important, and we're supposed to put the coffee pods onto that cardboard tray. There's room for the coffee pods on there, but there's a Coke can in the way, and so the system looks, it reasons, and then it, like, sanely moves the Coke can out of the way. So that's like what it should do, right? Okay, and you know, the same code and the same everything, it runs on different robots. I think the next example is another different robot. Yeah, so here we go, you know, same code. We tell it this time, well, put the screws in one container and the nuts in the other one, something like that. And it has to take a minute, it has to look and make a plan, and then it can do it. Okay. So I want to contrast that for right now with a system called Pi 0.5. So this is a model-free system that maps images directly to the motor controls. It's made by a company called Physical Intelligence, Pi. They now have a better model, but it's not available to us to try out, so I can't actually show that to you. But this is a pretty recent model-free approach in the sense that it maps images directly to actions. So I'll show you kind of directly. So here's a problem. We say place the peanut butter crackers into the tray. So their system is way more reactive. Like, it instantaneously starts doing stuff, and that is really an advantage of the model-free approach. But it sort of, and our guy had to think for a little while, but then it did the thing. And this ends up not actually working out very well. So here's another example, right? Put the medicine into the box, and that system immediately figures out what thing is the medicine, which is really very cool. It goes over there, it has a little trouble like getting together and focusing on grasping, but it also doesn't have a model of where the other objects are, really, and so it moves those other things out of the way. Our guy took a little while longer. So it's interesting, right? It's interesting to try to understand what are the strengths and weaknesses of these methods, and how can we train low-level control strategies for doing some of the things that are very hard to reason about, but how can we use reasoning to be much more general in the cases where we can. So we're exploring this also in humans. So at least in some cases, it feels like the model-based strategy can work a bit better in robots. So what about in humans? Do humans do things model-based or model-free, or for what kinds of problems do they do which way? Okay, so this is work that Nancy's student Ariane has been doing. So I alluded to this at the beginning. Here's a scene with some objects in it. They're kind of, these are at least objects that you might have seen before. And we tell you when orange has been dropped at random on the table, what object is it most likely to be behind? And actually, they're running human subjects in a VR setup so that people have to actually move an object out of the way. And in 3D, it seems very vivid, and you can move something, and they're recording a bunch of things as the people are doing this. And they're also looking at the case where the objects are not like culturally obvious objects, and so you might imagine that it's harder to like do completion. And in fact, when we run computer algorithms on these things, that doing completion on these weird objects is much trickier. But okay, so here's a little movie of a person, right? In this case, they're looking for a banana. It's similar to looking for an orange, and so a person in VR is like moving the objects, trying to find the thing. Okay, so we can ask, well, what kind of computational best predicts the human behavior? And I'm gonna, we'll show you, these are kind of preliminary results. We haven't actually finished all the work here to do this. But first of all, we can measure, you know, how well humans perform at moving the best object. If we pick objects at random, it's no good. If we pick the object that looms largest in terms of pixels in the screen, right, that doesn't work either very well. If we ask GPT-5, what object should we move out of the way, that doesn't work too well either. If we use this approach where we run the image through our 3D shape completion pipeline and then do some explicit spatial reasoning that says which one of these objects occludes the most volume, or occludes a volume that could hide the most oranges in a way, then we get surprisingly much behavior. What we're working, or better behavior, what we're working on right now is actually training a neural network model that just goes from the pixels to the objects, but that's not done yet. We think that it probably won't work as well as the model-based approach, but we'll find out. So, okay, where do we go from here? Well, we are thinking about, more generally, what's the structure of an intelligent agent, right? So how can we think about not just how do you do this one problem, how does perception interact with control in this kind of short-term thing, but really, what's the structure of a whole robot? That's the thing that I worry about a lot. And a thing that Nancy worries about a lot is what's the structure of a whole brain? If you look at brains, they're not uniform goo. Different parts are wired up in different ways, and even in the parts that have the same kind of wiring, they find that there's a lot of localization and specialization. And so specific parts of brain actually account for very specific kinds of function or aspects of processing and so on. And so it's really an interesting question to ask, can we robot people learn something from the modularity and structure of brains? Or can the people who study brains be inspired by some things that we know about algorithms and data flow and so on in robotics? And so, this idea of modular design is really important, right? And from the engineering perspective, if you have individual modules, you can test them and validate them independently. You can take the log of the amount of training data you need by training modules individually if they compose appropriately. And if we potentially learn different pieces of knowledge or ability, if we, for instance, learn different skills, we can compose them in new ways, in novel ways. We know how to do that in language, and we can do that in behavior as well. So, and the other important thing is that different aspects of intelligence, different aspects of reasoning, seem, in the brain at least, to have some different kinds of structure, of patterns of wiring. And that argues maybe that they should have different algorithms in the computer implementation, and that maybe it shouldn't be a kind of a monolithic neural network that's all the same from beginning to end that we train to do this job. So the steps that we're taking going forward, one is to think about what to do when there's partial observability. So a thing that we've been doing on the robot side is thinking about, how do we explicitly gather information? In the case, right, this object, the robot is supposed to put a magenta object on a blue one, so it's looking around. It has, the camera is in its hand. That's why it's doing this crazy dance. So we have this going in simulation, and we spend some time working on getting it to work in the real world. We're getting somewhere with that. A thing that Nancy's group is looking at is trying to understand more dynamic tasks. So not just like which object would you move out of the way, but in this case, they drop a ball in a crazy maze, and the person has to catch it. And so there's a lot of interesting behavior and dynamics in how the person moves around in anticipation of the ball coming down the chute. So that's another task that she's looking at. And we're going to start actually, I think, a kind of a reading group to study modularity in brains and in robots, and to try to think about how they can inform each other. So with that, I will say thank you, and I'm happy to take some questions. So thanks. If anybody has questions.
Just a small
Sure.
question. On the video of the robot picking the pills or picking the can, whatever, the information that he has as an input is on the video that we are seeing, or he has a camera?
There's a camera in the hand. Yeah. That's the same setup that the Pi was trained on. So it's exactly the same I/O spec as the Pi 0.5. Yeah. Yep.
So you call the Pi 0.5, what do you think about approaches that attempt to generate video plans and then execute based on those video plans? In your mind, is that a model-free or model-based approach?
Good. I mean, So as soon as you start poking, the labels fall apart, right? So I would say, I don't know, maybe no, certainly it's model-based, I guess, I would say, in the sense that there's a predictive model of what's going to happen as a function of what actions I take. Yeah, so there's transition. I think the word model, okay, the word model now is just totally useless, right? And I shouldn't really use it either, probably, because it just means so many things to so many people. There's the question of, do you have a transition model? So I would say that system has a transition model. Do you have a 3D model of the world? That's a different kind of model. That system doesn't, ours does. So we should probably just be more fine-grained in our conversation about that.